Okay, so here is an interesting application of harmonic functions to a thing that you're probably not expecting. That thing is the fundamental theorem of algebra. Now, there's several ways to state the fundamental theorem of algebra. I'm just going to state it this way. Um, all, not alley, all polynomials um, in, not of, in the variable z, in the variable z, so this would be like a complex number, have at least one complex root. Okay, and then of course we can reduce this to the real case, or we can derive the real case from this. If I have a polynomial and a variable x, I just replace x with z and I'm going to have a real root. Okay. Sorry, not a real root, a complex root. Okay, so how in the world are we going to use harmonic functions to prove this? Well, we're going to do it basically in 3 stages. Maybe the green marker will be okay for a borderline here. So stage 1, I should have looked up how to say this name. Stage 1 is prove Louisville's theorem. So what does that say? This says that if u of xy is harmonic, if u of xy is harmonic and bounded, on R2, then u is constant. So it's just going to be equal to some constant. So u is constant. Okay, so let's think about why this might be true. Well, what do we know about harmonic functions? Their maximums occur. So when I say u is bounded, I mean, um, yeah. So what do I mean by u is bounded? Well, no, I don't need to explain anymore. Bounded means bounded above and bounded below. So harmonic functions achieve a minimum and a maximum at the boundary of the domain. What is the boundary of the domain of R2? There really isn't one, but maybe we kind of think about infinity as being the boundary. And so it kind of is counterintuitive to our understanding of harmonic functions if it were to be bounded, because then it seems like, though, if it's bounded over all of R2, this seems to sort of violate the principles of the maximum principle, which says that a harmonic function does not attain a maximum or a minimum in the area that it's harmonic. Okay, now that's sort of a reason for why this might be true. That's clearly not a proof. So I will let you mostly think about how to prove this, but I will give you just one helpful hint. Or I don't know if it's helpful or not. You let me know if it's helpful. But the way that I thought about this, so hint. Now, sometimes the hint is the absolute worst way to solve a problem. I don't know if that's the case here, but I'll give you my hint. My hint is to show, let's see, I'm trying to think about exactly how much I want to tell you. The hint is to, uh, so you want to show u is constant, so I will write something down here. I'm going to write down directional derivative. And as long as I'm standing with my hand on the board, this will be the signal. I'm going to give you a little more information about what you should do in this hint. And so if you want to think about it on your own and don't see the hint, you can just fast forward the video. So in just a moment, I'm going to start explaining. Okay, so you want to show that the directional derivative at every point in any direction is zero. If the directional derivative if the directional derivative at a certain point is equal to zero, it means that if I move in any direction, the function is not changing, at least infinitesimally. If the directional derivative at every point in every direction is zero, it means the function is not changing anywhere. This is very similar concept to when we use the method of characteristics. Okay, so how can you show that the directional derivative is? How can you show that the directional derivative is zero? Okay, so now I'm gonna do two hands on the board now and give you a little more of a hint if you want to know. And when I take both of my hands off, then I'm going to be done. So how can you show the directional derivative is bounded? Well, you're going to use the fact that if u is harmonic, then its x derivative and its y derivative is harmonic. And so in other words, what you can do is you can write the directional derivative of u as you can use the mean value theorem to write the directional derivative of u as an integral over the boundary of a circle, and then you can use, not an integral over boundary of a circle, an integral over a circle. Then you can use Green's theorem to convert that to an integral over the boundary of a circle. Then you can use the bounds on u to show that that is going to be bounded by some constant over r. So in other words, where r is the radius of the ball. So in other words, you can show that the directional derivative of u at any point in any direction is going to be less than or equal to like 1 over r, or some constant over r. For an arbitrary r, let r go to r go to infinity. That proves the directional derivative is 0. Sorry if that last part was getting kind of confusing. This is a very uncomfortable pose to be in. Okay, so now we're back at it. So that's my hint for this part of the problem. So what is part 2 of the problem? Part 2 of the problem, so let's say I'll put a boundary here. So part 2 has kind of maybe several things going on. You're going to show that different functions are harmonic. So you want to show that polynomials in the z variable, so f of z is equal to the sum k equals 0 to n. We'll say ak is a constant, a complex constant, times z to the power of k. Show this is harmonic. So that's harmonic. I don't know if that's going to be directly applicable. This is like part A. Part B is to show that 1 over f of z is harmonic. Okay, now that one might be a little tricky, but definitely still doable. And then, so that's step 2. That's also going to be a little challenging. That has nothing to do with harmonic. Well, I mean, that has nothing. I was going to say that has nothing to do with harmonic functions. I'm not really sure what I meant by that because I'm asking you to show that it's harmonic. I think what I meant by, well, I just don't know what I meant. And then step 3 is going to be where you put these two pieces together. And step 3, you're going to put these two pieces together and argue. You're probably going to start off, even if you don't end up this way, which I think you probably will, argue by contradiction. For the fundamental theorem of algebra. Okay, so what would the contradiction be if p of z is a polynomial with no roots, no complex root, then there's a contradiction. obviously you're going to have to find the contradiction. I'm going to move out of the way in a minute. Okay. Now, this obviously you can look it up online and find what all of this on your own. But I think it would be interesting if you at least spend some time thinking about it. If you are in my 696 class in the summer, or if you will be in my 696 class in the fall, we're going to see a magnificently beautiful proof of this theorem right here. The reason that I like, well, there's a number of reasons that I like to show this proof. One is because it's just very nice, and the other reason is that it doesn't involve any mathematical symbols that I can remember. It's just a paragraph, no mathematical symbols at all, very short, yet it proves this wonderful theorem here. And that theorem is due to Edward Nelson. Great proof by Edward Nelson sometime a long time ago in the Proceedings of the American Mathematical Society. Okay, so this over here, so if you go and start looking up stuff online, which is fine, I don't mind that. If you go and start looking up stuff online for this kind of ideas of the proof of the fundamental theorem of calculus, what you're probably going to see over here for this part is lots of stuff about complex analysis. Okay, lots of stuff about complex analysis. And the connection, the reason that there's a connection is because if you have an analytic function, the real part of an analytic function and the imaginary part of an analytic function are harmonic. And so over here, essentially what we're going to, so when we say 1 over f of z is harmonic, this needs a little bit of care. What we mean by harmonic, because if f of z has a 0, there's going to be a problem there. So show this as harmonic, I guess, wherever it's defined. So if f of z is analytic, 1 over f of z is analytic. It's not necessarily true with harmonic, though. So you're going to have to use a special structure of the polynomial here to prove this fact. I think that's all that I want to say. I hope this is going to be an interesting thing for you guys to think through, even if you end up having to just look it up. I hope, I mean, there's nothing wrong if you just have to look up the entire proof for this, but I hope this will be interesting, especially to those of y'all who are going to be teaching high school students. I don't know what how the fundamental theorem of algebra is typically proven. Obviously, we're proving it in a very non-algebraic way here, but that's one thing to think about. The other thing that I want to point out is, so just sort of as an advanced idea here, we're saying all polynomials in the variable z have at least one complex root. Well, to what extent can this be generalized? I don't really think too much about things like this, but generalizing a theorem like this, I think, will either get you something wrong. Well, you can either generalize this theorem to being wrong, in other words, it's not an actual theorem, or to being trivial. So I'll let people who talk more about algebra to talk about things like that in the discussion forum. So this is why a lot of people, I think this may be one of the reasons a lot of people say this really isn't a fundamental theorem, simply because it's stated this way kind of only makes sense for real and complex numbers, or polynomials with complex roots or real roots or something like that. At any rate, that's all that I have. I hope you guys enjoy this, and I hope it's one of those things that you didn't expect to see in this class, but you're like, hey, that's pretty cool, so you let me know.